Um, yeah, so I'm going to be talking about playing repeated games, which actually does end up being related to boosting, because no matter what I do, it always comes back to boosting, but we'll get to that later. So the talk is really about two different topics. It's about machine learning, and it's about game theory and how those two come together, or one way in which those two come together. They actually come together in lots of ways. We're really just going to look at one of them. So the first topic is machine learning. So machine learning is a field that tries to identify automatic algorithms for, in some way, learning to do something better, learning to make better predictions, learning to make better decisions, learning a skill of some kind, and doing that through observation or experience from data often. So here are three examples of that. So the first one is learning from a whole batch of training examples to detect faces in images. So given a picture, a photograph, does that image, is it a picture of a face or not? The second one is more of a sequential problem where you're trying to sequentially predict what a person is going to do. Say, trying to predict whether a person is going to click on a link on a web page or not. And then the third one is something even still more different, which is trying to get a computer to learn to drive a car, a toy car, maybe someday a real car, by observing how a human does it. So kind of an imitation problem. So if you haven't looked at learning before, you might look at these and say, well, they're all basically the same. They all involve learning. But if you're somebody like me who works in the field, you look at these three problems and think that they're all rather different. So the first one involves learning from examples, learning to classify things from examples. Is it a face or not a face? The second one also involves classification. You're trying to say whether the person is going to click on a link or not. That's a kind of classification. But it's more of a sequential problem where you're making these decisions one at a time, and there's an opportunity to learn in between each one of those. And then the third problem is really something quite different where you're learning a skill. You're not doing classification at all. So machine learning comes in many different flavors. Now the second topic we're going to look at is game theory. So game theory is a field which studies interactions of all different kinds between all different kinds of players. So it looks at ordinary games like checkers, tic-tac-toe, whatever. But it also looks at a lot of other kinds of interactions as well. So how do people interact, corporations, animals, species? Many of these interactions can be modeled using game theory or studied using game theory. Now, we're going to be looking at the interactions between learning and game theory. And there's already you can already imagine what some of the connections are going to be, because learning often involves some form of interaction. For instance, there's the interaction between a teacher and a student. And on the other hand, games are often most interesting when some form of learning is involved. So, you typically don't play a game once, you typically play it over and over again, and you get better at the game, or you get better at figuring out what your opponent does. Okay, so in this talk, what we're going to do is we're going to look specifically at one connection between learning and game theory. I'm going to describe a general algorithm for learning to play repeated games. Repeated games means where you're playing it over and over again. And then we're going to see how we can apply that one algorithm to handle a whole bunch of different learning problems. In particular, all three of the learning problems described up here, we're going to see how we can handle all three of those using that one algorithm. Okay, so this is showing that the algorithm is very general, and it's also reveals some connections between these problems that might not be immediately evident. So it's going to reveal some underlying connection, some structure that's there that might not be obvious. Okay, so here's an outline of the talk. So the talk is really in two parts. So in the first part of the talk, I'm going to go into a fair amount of detail on this algorithm to play repeated games. So if you don't know anything about game theory, I'm going to start right at the beginning. If you do know something about game theory, you might be a little bored for a couple minutes. But in any case, we're going to start at the beginning and go into some detail on how to play repeated games with the theory and the algorithm. And then the second part of the talk is going to be more high level, and we're going to see how to apply that algorithm to 3 different learning problems: boosting, which Jen mentioned, online learning, and apprenticeship learning. Okay, so how to play repeated games. This part of the talk is joint work with Yoav Freund. Actually, the first 3 parts of the talk are joint work with Yoav. And then the last part is with Umar Syed. Yeah. Yep.
We normally learn to distinguish between adversary opponent and neutral opponent. Are we going to forget about the distinction when we talk?
Let me come back to that, okay? So, yeah, so that's one of the things I want to talk about. Okay, so as I said, we're going to start right at the beginning with what a game is. So for our purposes, a game is described by a matrix M. So like everybody else who starts talking about game theory, I'm going to start with the classic game rock, paper, scissors, because it's small. So in this kind of a game, there are 2 players. There's the row player, who I'll be calling Mindy, and you'll see why in a minute, and the column player, who I'll be calling Max. And to play the game, Mindy, that is the row player, chooses one of these rows, and simultaneously, at the same time, Max, the column player, chooses one of these columns, and then the chosen entry gives the loss to Mindy. Okay, so for instance, if Mindy chooses paper and Max chooses scissors, then that gives us this entry over here, okay, which is a loss of 1 because scissors cut paper, so Max wins, which means that Mindy loses. So we're always going to be taking Mindy's point of view, okay, in all of these descriptions of these games. We're viewing ourselves as Mindy, and Max is our opponent, our adversary, okay? And we're going to assume without loss generality that the entries are between 0 and 1. So this might seem like a very limited kind of game if you haven't seen this before, but in fact, in principle, even large games like tic-tac-toe, chess, Monopoly, whatever you want, all of those games in principle can be put into this matrix form, although the matrix would be extremely large. We're actually going to be later interested in very large games, as we'll see. Okay, so that's the game. That's what a game is. Now, I assume this is mainly a computer science audience. So in computer science, we often use randomization. And the same is true in game playing, that it will often be natural for each of the players to play in a randomized fashion. So in that case, Mindy, rather than choosing a single row, would instead choose a distribution P over the rows. And the interpretation is that the actual row that she picks is chosen at random according to that distribution P. And then simultaneously, Max chooses a distribution Q over the columns. So then Mindy's expected loss, in that case, we can compute the expected value, well, in the straightforward way, just add up over all rows and columns, ij, of the probability of choosing that row times the probability of choosing that column times the resulting loss, and that gives us Mindy's expected loss, okay? And we can write that more conveniently in matrix form, and I'm often going to write it like this, M of PQ, okay? All right, so just a bit of terminology. So these individual rows and columns are called pure strategies, and these distributions over rows and columns are called mixed strategies. And I'm letting m, little m, be the number of rows of the matrix. And I don't have notation for the number of columns because we're actually not going to need it. Nothing is going to depend on the number of columns. Now, one thing I forgot to mention is what Max is trying to do in all this. Mindy, of course, is trying to minimize her loss. Max, for now, think of Max as being an adversary. Max is trying to maximize Mindy's loss, which is why she's Mindy. She's trying to minimize it, and he's Max. He's trying to maximize it. But later, we're going to come back to that point, and we're going to change that. Okay? And do interrupt me with questions also. Okay. Oh, just one more tiny bit of notation. So we have m of PQ for the expected loss if Mindy plays with mixed strategy P and Max plays with mixed strategy Q. Sometimes one of them will play with a pure strategy, say I, and Max will play with a mixed strategy Q. And in that case, we just write m of IQ for the resulting expected loss, and similarly m of PJ for when Mindy plays mixed and Max plays pure. Okay? Now, these are really expected losses, but I'm often going to just refer to them as loss. Okay? Okay. So that's randomized play. Now, so far, I've been saying that they play at the same time, simultaneously. What happens if one of them plays first? What happens if Mindy plays before Max? So she decides what to do, announces it, and then Max plays. Well, let's suppose that she chooses to play with mixed strategy P. Well, what's Max going to do? Well, if Max is actually trying to minimize Mindy's loss, then he's going to choose that mixed strategy Q, which maximizes the resulting loss, m of PQ, right? So then her loss, if she plays P, is just going to be the maximum over Q of m of PQ, right? And we can view it as a function of P. Okay, well, so it's almost like Mindy knows what Max is going to do for any choice of strategy P. Oh, sorry, I forgot to mention this. I forgot to mention to notice that this maximum is actually a linear function in Q, which means that even though it's a maximum over distributions, it's actually going to be realized, this thing is dying, realized at a single column J. Okay? So just a small little fact. Okay, so coming back to what I was saying, so it's like Mindy knows what the resulting loss is going to be, right? It's just a function of P. So she's going to choose her mixed strategy P to minimize the resulting loss, which will just be the minimum over all these mixed strategies P of the resulting loss L of P, which we can write out as just this min-max. Anybody, you don't have a better pointer, do you? Okay. Okay, which is just min-max, right? So this is what's going to happen if Mindy plays first. Well, we can make the same argument if Max goes first. By the exact same kind of argument, if Max plays first, then the resulting loss will instead be max-min. Okay? Okay, so which is better, playing second or playing first? Well, clearly, it's better to play second. It's better to play with more information than with less information, right? I mean, if it's better to play with less information, all you have to do is pretend that you never even got the information, right? Okay, so this again is Mindy's loss if she plays second, and this is Mindy's loss if she plays first, and she's trying to minimize the loss. So what that says is that this side should be at most this side, right? Playing first should be at least as bad as playing second. Now, if you haven't seen this type of thing before, you might naturally believe that, at least in some cases, playing second is going to be strictly better than playing first. Surely getting more information should be better than not getting that information, at least in some cases. And you would naturally believe that at least in some cases, this should give strict inequality. It turns out that that's not true. So von Neumann's min-max theorem, very famous theorem, says, in fact, that the loss will always be the same. Whether Mindy goes first or Max goes first, the loss will always be the same. So it's saying, it's saying that there is no advantage in any game to playing second. Okay? It doesn't matter whether you play first or second. If both players are playing optimally, the loss will be the same. Yeah?
So that's assuming a mixed strategy, right?
Yes, this is only for mixed strategies. It's not true for pure strategies. It's not true for pure strategies. It's not true for arbitrary functions. If you replace m by an arbitrary function, it's not true. But in this setting, where you have mixed strategies and a matrix, it's true. Okay, so the min-max theorem, again, says that this min-max always equals max-min. And their common value that you get here is called the value of the game. And I'll always be denoting it by little v in this talk. Okay, so that's the value of the game. And it really tells us how each of the players should be playing the game. So in particular, we're going to be especially interested in the strategy P star, which realizes the minimum over here. Okay, that strategy P star, which realizes this minimum, is called a min-max strategy. And likewise, the Q star, which realizes this maximum over here, is called a max-min strategy. And those strategies are optimal. They're optimal in this sense. So the fact that P star is a min-max strategy, the fact that it realizes the minimum up there, means that if Mindy plays with strategy P star, then her loss cannot be more than the value of the game V, regardless of how Max plays. And that strategy is optimal because there's a way for Max to play, namely using this max-min strategy Q star, so that he can always force her to have loss at least V. So there's nothing that she can do which would allow her to do strictly better than V. And if she plays with P star, she'll never suffer loss more than V. So in that sense, P star and Q star, these min-max, max-min strategies are optimal. Okay, so as a concrete example, in rock, paper, scissors, the min-max, max-min strategy is just to choose rock, paper, scissors with equal probability, probability 1/3 for each one. And if you think about it, if I'm playing that way, if I choose rock, paper, scissors with equal probability, it doesn't matter what you do. My loss will always be the same. I'll always win or lose exactly half the time. Okay. And the computational problem of finding a min-max or max-min strategy is called solving the game. So to solve the game means to find a min-max or a max-min strategy. Okay, so everything I described up until now was classical game theory dating back, I don't know, I think to the 30s. And it seems to fully answer how to play games. All you do is you compute the min-max strategy if you're Mindy, and you play with that min-max strategy, and that's it. And you can find the min-max strategy, for instance, using linear programming. Turns out to be a linear programming problem. Okay, but there are a number of weaknesses. So first of all, the game matrix M might be unknown. You might be playing a game where you don't know the entire matrix, or maybe you don't know any of the matrix until you start playing it. Or the game matrix might be huge. It might be so big that you can't use linear programming. Or, and this comes to your point, it might be that the opponent is not fully adversarial. So all this theory is predicated on the assumption that we are playing against a maximally adversarial opponent, an opponent who plays optimally, who wants to maximize our loss, and who is smart enough to know how to do it. And it's often the case that we might be able to do a lot better than the value of the game if we're playing against a non-adversarial opponent. So my favorite example of this is from The Simpsons when Bart and Lisa were playing rock, paper, scissors. And before they play, Lisa thinks to herself, poor predictable Bart always takes rock. And Bart is thinking to himself, good old rock, nothing beats that, right? So if Lisa was paying attention to all this classical game theory, then she would just play rock, paper, scissors, each with equal probability, and she would win or lose with probability 1/2. Whereas, obviously, if she's playing against Bart, she can do a lot better by always playing, I guess, paper, which always beats rock. Okay, so if we're only playing this game once, then it's completely hopeless to overcome what we don't know about the game or what we don't know about our opponent. But if we're playing the game over and over again, if we're playing the game repeatedly, then it might be possible to learn to play well, to learn over time to play well. So the goal now, in what I'm going to talk about, is to figure out how to play almost as well as if we knew the game ahead of time, and as if we knew everything there is to know about our opponent ahead of time. Okay, so we're going to play it repeatedly, but over that, starting out not knowing anything about the game or our opponent, and over time we want our performance to be almost as good as if we did have full knowledge at the beginning of play. And it turns out to be possible. Okay, so here's the setting in slightly more formal terms. So we have this game matrix M that we're playing, and initially the game is unknown, entirely unknown. And then we're going to play the game capital T times. And each time the game is played, well, kind of the natural thing happens. So Mindy decides what she's going to play on that round of the game. Okay, so she's going to choose a mixed strategy PT. And then Max chooses a mixed strategy QT. And here we're giving Max extra power. We're allowing Max to know the game M, and we're even allowing Max to know the mixed strategy PT that was chosen by Mindy. So Max can choose QT with knowledge of PT. Okay? And then once they've chosen their strategies, PT and QT, Mindy's loss is just the natural thing, the resulting loss M of PT QT. And then we allow Mindy to find out something about the game matrix. Okay, so there are different models, there are different things that we could allow her to observe about the game matrix. So in this talk, we're going to allow Mindy to observe what her loss would be if she had played any other pure strategy or any of the pure strategies. So we allow her for each pure strategy I to find out what her loss would have been if Max had played distribution QT. This is my punishment for playing with my cat with this thing. Now it's dying. Okay, so for instance, it's often the case that Max will choose a single column. QT will be concentrated on a single column of the matrix. And what this is saying in that case is that Mindy gets to observe that entire column of entries. Now, if this seems like we're giving her too much information, then there's been a whole body of other work done where she gets a lot less information. But this fits what I'm going to talk about later. Yes?
So the strategy still remain unconditional on what you saw. You choose
For Mindy?
for Mindy.
No, Mindy can do whatever she wants to.
But PT means it is a probability distribution,
Right.
which is a function of the sequence.
Which is a function of, well, it's a function of all the information that she's getting. Okay, so Mindy's allowed to learn. She's allowed to learn from these observations and to change how she plays according to those observations. Max, on the other hand, is allowed full knowledge of the matrix and full knowledge even of PT. Okay? Okay, so here's what we want. I said before that our goal is for Mindy's performance to be almost as good as if she knew the game matrix and if she knew everything there is to know about the opponent. So everything there is to know about the opponent, by that I mean that as if she knew ahead of time what her opponent was going to play. If she knew the exact sequence of QTs that was going to be chosen by Max. Okay? So this is the kind of property that we want this algorithm to have. Okay, so what we have over here on the left, this term is Mindy's loss on round T, her actual loss when she actually played the game. And here we're just taking an average over the T rounds. And so this is her actual average loss. Now over here, what we're doing is we're fixing the QTs. We're fixing the QTs, which are the actual plays chosen by Max. And we're looking at her loss if she had played using a strategy P, a single strategy P. And we're allowing her to choose any strategy P that she wants, but we're insisting that she use that same strategy P over and over again in each of the T rounds. Okay, so in that case, this is the best loss with the restriction that she always play with the same strategy on all T rounds. Okay? And it's the best chosen in hindsight, as if she knew all of the QTs ahead of time. And what we want is for her actual loss to be not much worse than this best loss in hindsight, plus some small additional amount, which is called the regret. All right? So this is the type of bound we're looking for. Okay, so here's an algorithm that does that. Yeah.
What the motivation, why she has to, why do you compare it to sticking to a constant target?
So why does she have to play the same thing over and over again? Well, first of all, if you allow her to change every single round, then that's really impossible to compete against. Okay, because like if you're playing rock, paper, scissors, for instance, and you actually know what your opponent is going to choose on every round, then you can get loss 0, and it's just impossible to compete against. Okay, so that's one answer. There's also been other work where Mindy is allowed to switch a few times, like she can use one strategy P for a while, and then she can switch to another one, and then switch to another one. So these are all later enhancements to the model that can be made. Or you could imagine Mindy choosing her strategies according to some class of rules of some kind. Again, there are various other enhancements, but this is kind of the first simple problem to try to solve. Okay, so here's an algorithm. This is called the multiplicative weights algorithm, or MW. Very, very simple algorithm. This is an algorithm for Mindy that Mindy can use to play this game. Okay, so this has a single parameter eta, which is a positive number. And so to play the game, all Mindy has to do is choose these distributions PT, choose these mixed strategies PT. Okay, so on the first round, she knows nothing about the game, so she just chooses the uniform distribution for P1. And then on every round T, what does she do? Well, on that round, she played using PT, and she observed losses for each one of the pure strategies, for each one of her rows. So all she does to compute this new strategy, PT plus 1, is for every row I, she takes the old probability of choosing that row and multiplies it by e to the minus eta, where eta is this positive number, times the loss that would have been suffered if she had played with that pure strategy. Okay, that's what this MIQT is. Okay, and then once she gets done multiplying all these numbers, she won't have a distribution anymore, so she just normalizes so that these numbers add up to 1. All right, so the idea is really very simple. The intuition is very simple. All she's doing is she's decreasing the weight of the strategies that are suffering the most loss. So the bigger the loss that would have been suffered for a particular strategy or row, the more she cuts the weight of that row. Okay? And the less the loss, the less she cuts the weight, so that after you renormalize, the effect will be to actually increase the weight of the ones that suffer less loss. All right? Okay, so this algorithm is, it's a generalization of Littlestone and Barmuth's weighted majority algorithm, really just a direct generalization. And there have been other algorithms for this problem. The oldest ones are due to Hannon and Blackwell, which go back to the 50s. Okay, so here's what can be proved about this algorithm. So basically, we can prove the kind of bound that I had on that earlier slide. So we can show that for any game M with little m rows, and for any opponent at all, it's possible to choose eta so that her actual average loss will be this best average loss plus this additional term delta t, which is a number. It actually works out to be something like this, O of square root log m over t, which you'll notice is going to 0 fairly quickly, going to 0 at the rate 1 over root t. Okay, so the regret is getting small, and it's saying that even without knowledge ahead of time of the game, she can do almost as well as if she knew the entire game ahead of time and knew the opponent in this sense. Okay? Now, this best average loss, it's not hard to show that this is at most the value of the game. So it's saying that she'll never do a lot worse than the value of the game. But it leaves open the possibility of actually doing much, much better than the value of the game as well. And in terms of this regret, you'll notice that the regret is very moderate in terms of the size of the matrix. It's only logarithmic in the number of rows, and it's completely independent of the number of columns, does not depend on the number of columns at all. And likewise, the running time of the algorithm, just of the MW algorithm, okay, is linear in the number of rows of the matrix, and again, independent of the number of columns. So this is a reasonable algorithm to use on extremely large matrices, which we're going to take advantage of soon. Okay. Said that already. Okay, so I'm not going to prove that theorem. It's actually, the proof is not that hard, but I don't have time for it. But instead, what I did want to show you is an interesting corollary of this analysis. So we can use the MW algorithm and its analysis to actually prove the min-max theorem that we talked about before. So I don't know, personally, I always like it when you can use an algorithm to prove a mathematical theorem. Okay, and in this case, we can do it very easily. Okay, so again, the min-max theorem says that this min-max equals max-min. Now, we already argued that min-max is at least max-min. That's not that hard. The hard part is showing that min-max is at most max-min. Okay, so to prove that theorem, we're going to imagine that Mindy and Max are playing this game repeatedly. And so we have to give them certain strategies. So Mindy will play the game using MW. And Max will play the game in kind of the most obvious way you would immediately think of. Okay, so remember, Max knows PT, right? And so the natural way for Max to choose QT is to choose that strategy which would maximize Mindy's loss on that round T, right? That's the most obvious natural thing for Max to do. So imagine that Mindy and Max are playing the game in this way. And I just need a tiny bit of notation. I'm just going to write P bar for the average of the PTs and Q bar for the average of the QTs. Okay? Just a little bit of notation. Okay, and here goes the proof. Okay, this is the only proof I'm going to do in this talk, but it's a nice short proof. It's all going to fit on the slide. Here's the first line, min-max is at most, and the last line is at most max-min. Okay, and it's all going to fit on that one slide. Okay, so here we go. And I'm using this matrix notation. Oh, actually, I'm not going to prove exactly this. I'm going to prove something a tiny bit weaker. I'm going to prove that min-max is at most max-min plus this regret delta t. But because delta t can be made as small as we want just by making t large, that's still going to prove the theorem. Okay? Okay, so here goes the proof. Okay, so the first line says min-max of this thing is at most what we get when we take that p that minimizes this expression and replace it by p bar. Okay, and that's true just because this is a minimum, right? So it has to be true for any particular p, in particular p bar. Now we're just going to take p bar, which is the average of the PTs, and plug it in here. Okay? And now we're going to notice that if you take this max of the entire average, that's at most what you get if you take the max term by term rather than all at once. You know, you maximize each one of these terms separately. Or if you like, you can do it based on convexity. Okay? And now we remember that Max is choosing QT to maximize exactly this expression. So, right, QT maximizes this, so we can just replace it with equality. And now, this is really the key step. Now we can use that analysis of the algorithm, because this is Mindy's loss, right? This is Mindy's actual loss when she plays the game. And the theorem that we had on the last slide said that's at most the loss what we get when we minimize over p, you know, we choose that best loss, plus this regret delta t. But now the last two steps, we see that this has the average of the QT, so we just replace it with Q bar. And then finally, this is, you know, this is for a particular Q bar, so that's at most what you get when you take the maximum Q. And that's it. So that's the entire proof, all on one slide. Yeah?
Sort of, you said without hesitation that Max's strategy, the best is to greedy, to maximize the loss per round.
To max, yeah. Yeah, well, I have to say when we...
He knows how to win his strategy. He breaks it to some place that he can get much better. So he did convince that this is the best strategy for him.
Oh, okay. So you're saying that...
He knows the algorithm.
Yeah.
You say he will do the greedy step.
Okay, well, I'm just...
Convinced that this is the right argument.
Oh, I'm not saying that this is necessarily the way for him to maximize her loss. I'm just saying that it's a natural strategy that he could use. You know, probably the most natural thing that you would think of as a strategy for him. But you're right, it does, and the argument doesn't require that it be the one which maximizes her loss overall. It doesn't depend on that. You know, the argument only uses him maximizing things term by term, or round by round. Okay. Okay. Now, okay, so here's a theorem. It's not exactly a new theorem. Goes back to the 30s, I think. But what's what's useful about this argument is it tells us something about this algorithm. It actually tells us an important property of the algorithm. Because suppose we skip the first step of this argument. Okay, so we just blot out that first step of the argument. What is this chain of equalities and inequalities telling us? It's telling us that if Mindy plays with p bar, then the maximum loss that she can suffer is at most this max-min expression, which is the value of the game, plus delta t, plus this small amount. So let me just take that and rewrite it again on the next slide. Again, what it's saying is that Mindy plays with p bar, then the maximum loss she can suffer is at most the value of the game plus delta t. Now, if she were actually playing with the min-max strategy, the most loss she could suffer would be v, the value of the game. This is saying she can do almost as well. The most loss she can suffer is the value of the game plus a little bit. So it's saying that p bar is actually an approximate min-max strategy. And by the same token, q bar is an approximate max-min strategy. So it's telling us that we can use this algorithm to approximately solve any game. We can use this learning algorithm as a way of approximately solving a game, which is something we're going to use in a minute. Okay, and also let me just mention that the QTs each of the QTs can be concentrated on a single column, which means that when you take this q bar, your approximate max-min strategy, when you take that average, it will be sparse in the sense that it will have at most t non-zero entries. Okay, also a useful property. Okay, so this concludes the first part of the talk. So let me just summarize what we've seen. So I presented this algorithm, the MW algorithm, plays almost as well as the best fixed strategy. It's very efficient. In particular, it's independent of the number of columns of the matrix. We proved the min-max theorem, and we showed that this algorithm can be used to approximately solve a game. Okay? So maybe, I don't know, before I go on, are there any questions? Yeah?
Mindy was receiving two types of information. The first one is the loss for every pure strategy, and the loss of her action. Why the loss of her action is not used in the algorithm?
Well, actually, she could compute that if she wanted to. So if she knows the loss for every pure strategy, then she can compute the loss for every mixed strategy as well, just by taking a weighted average of them. So she can compute that for herself if she wanted to. Yeah?
There wasn't an expression involving both p bar and q bar. If both players follow the approximate strategy, are each of them only better off than what's implied in what's involved? So, if I'm doing the bar strategy,
the only
and you also, my opponent also do the bar strategy, does that make me only better off than if you did?
I don't know. I mean, it will be, based on these general things, it will be somewhere between v minus delta t and v plus delta t, but otherwise, I don't know. Yeah.
Why is it called MW?
Oh, multiplicative weights, because you're taking these weights and multiplying.
What's the history of that algorithm?
It really is the Littlestone and Varmuth's weighted majority algorithm, just generalized to games, generalized to playing games. Okay, so so it kind of went from them, and then there was an algorithm in between there called hedge, and then to this algorithm. Okay, so the bulk of the credit goes to them. Okay, so what I want to do in this second part of the talk is to look at various applications. What time am I supposed to finish? How much? Ooh, okay, well, I'll pretend you didn't say that. I'll go for something less than that. Okay, so I want to talk about 3 different applications in less detail. So the first of these is to boosting, because I can't give a talk without talking about boosting. Okay, so Right. So for people who haven't seen boosting, let me just very quickly introduce it. So, so consider a particular problem like learning to filter out spam, which basically is the problem of learning to identify which email messages are spam and which are non-spam. So an approach to this problem is to start by gathering a large collection of email messages and to label each one as spam or not spam. Okay, so this first one, Rob, can you review a paper? That's undesirable but not spam. Earn money without working. Yeah, that's terrible. That's spam. Okay, so the goal is to have the computer learn from these examples to distinguish spam from non-spam. And if you think about a problem like this, well, then it's kind of, you can imagine easily coming up with rules of thumb that would often be correct. So like if the word Viagra occurs in the message, then predict that it's spam. Otherwise, predict it's not spam. Okay, and I'm sure everybody could think of 20 of these, no problem, right? So it's easy enough to find these rules of thumb. What's hard is to find just a single prediction rule which will be very highly accurate. So the idea of boosting is to somehow use these rules of thumb, gather a whole bunch of them, and somehow combine them into a single rule that will be very accurate. Okay, so I'm just going to give a very high-level description of how boosting algorithms work and really what the boosting problem is. So here's what we're given in boosting. First of all, we're given a set of training examples, like a collection of spam and non-spam emails. And then, secondly, we're given access to a subroutine, a so-called weak learning algorithm, which we can use for finding these rules of thumb, or what are called weak classifiers. Okay, so in the spam example, you could imagine writing a little program that would search for the best rule of thumb given some collection of examples. Okay, that's what I mean by a weak learning algorithm. And the output classifier is called the weak classifier, that rule of thumb. Now, what we're assuming implicitly is that we can always find these weak classifiers which perform a little bit better than random guessing. So like in that Viagra example, it's not going to be very accurate. It's certainly not going to catch all of your spam. But you could imagine that it's going to do something than just a rule which guesses randomly. Every email message that comes in just guesses randomly whether it's spam or not spam. So that's what we require of these weak classifiers, that each one be a little bit better than random guessing. Okay, so here's how boosting works. So again, the idea is to repeatedly train this weak learner or weak learning algorithm to get a weak classifier. So we're just going to gather a whole bunch of weak classifiers, and then we're going to combine all of them into a single final combined classifier. That's the high-level idea. Now, we can't just call this weak learner over and over again with the same data set, because you'll just keep getting the same weak classifier over and over again. So instead, in boosting, what we do is we repeatedly find distributions over the training examples. So on every one of these rounds, we find a distribution over the training examples, which kind of encodes which examples are hard and which are less hard, or which examples are important on that round and which are less important. And then we'll train the weak learner on that distribution to get the weak classifier. And so the whole problem is, how do you choose these distributions, and how do you combine these weak classifiers into a single combined classifier? So,
Then you set as examples, but they vary in frequency, or in virtue of frequency.
yes. So you're given a fixed set of training examples, but the booster, the boosting algorithm, is allowed to play around with distributions over them. Now, how to choose these distributions? Well, intuitively, we want to put the most weight on the hardest examples. We want to focus on those hard examples. And then how do we combine these weak classifiers into a combined classifier or final classifier? This natural thing to use is just to take a majority vote of all the weak classifiers. So each one gives you a prediction, spam or not spam. Just take majority vote, or a weighted majority vote. Okay. Okay, so that's the boosting problem. Now what I want to do is show you how boosting can be viewed as a game, or really just sketch it. So first of all, in boosting, there are two players. There's the boosting algorithm, the booster, and the weak learning algorithm. We're going to identify the booster with Mindy, the row player, and the weak learner we're going to identify with Max, the column player. Okay, so we're setting up this boosting problem as a game. Okay, so for the matrix, well, we're going to have one row of the matrix for each of the training examples, and one column of the matrix for every possible weak classifier. So there's going to be a huge number of columns. And then we have to say what the matrix is. So basically, we're going to put a 1 if, okay, so I and j, I is a row, or a training example, j is a column. So we're going to let that entry be 1 if that weak classifier is correct on that training example, and 0 otherwise. Okay, so this matrix is going to be really big, and all it's doing is encoding which weak classifiers are correct on which examples. And the thing to notice is that it's got a huge, huge number of columns, because there's 1 for every possible weak classifier, so gigantic matrix. Okay. So what does the min-max theorem say about this matrix? Well, what it says about this matrix turns out to be very closely related to the basis of boosting. Boosting is based on the assumption that I mentioned earlier called the weak learning assumption, which is this assumption that we can always do better than random guessing. It says for any distribution the booster can choose on examples, the weak learner is able to find a weak classifier whose weighted error is a little bit better than random guessing. If you just guess randomly, you'll be right half the time. This is saying that the weak learner can always find a weak classifier that's a little bit better than random. So gamma here is some small positive number. Okay? Well, it turns out if you work through all these definitions of what the value of a game is and how we set up this game matrix, it turns out that this condition is equivalent to the game having a value which is at least a half plus gamma. So this fundamental assumption to boosting is related to the value of this particular game. And what's more, the min-max theorem, again, if you work through definitions, I can't give you all the details because we don't have time, but the min-max theorem tells us that there has to exist a weighted majority classifier that will correctly classify all of the training examples. Okay, so again, just follows from all these definitions. So it's saying that if you have this weak learning condition, which seems like a very weak condition, by the min-max theorem, it tells us that there's actually a way to correctly classify all of the training examples. So at least we can do well on the training examples. And what's more, this particular classifier is defined by the max-min strategy of this game matrix. So it means that if we can solve this game, if we can find the max-min strategy, then at least we'll have a way of doing well on the training set. Okay, so this max-min strategy would do perfectly on the training set. How do we find it? Well, we've got this algorithm, the MW algorithm, for finding a max-min strategy. And so we can just apply that algorithm to this game matrix to find this max-min strategy. And if you do that, you end up with a boosting algorithm called AdaBoost, or actually it's a very slight variant of AdaBoost. Okay, but this is a way of deriving AdaBoost using this game theoretic setting. Yeah?
This all seems very nice, but it seems like the size of the number of columns is the killer. Let's take the game of Go, and you've got all the different possible permutations of all the different types of patterns that could occur in Go. It might be extremely difficult to decide to do the computation to find out that you're doing better than random and so on. And you've got lots and lots of columns to deal with.
Right.
And so the algorithm sounds really good, but could you comment on the
Right. So
issue?
that's right. So, so first of all, MW's running time is independent of the number of columns. Okay, so but the place where number of columns matters is we're assuming that we have an opponent who is choosing one of those columns. So we're passing this problem off to the, in this case, to the weak learning algorithm to choose which column. So we're really depending on this learning algorithm as an oracle for selecting one of the columns. And otherwise, everything is efficient, and the regret bounds and computation time, none of those things depend at all on the number of columns. Okay?
Do you have to consider really all possible weak learners? How about if the space is continuous, like linear classifier?
Yeah, so again, you can have an infinite number of columns, but again, what we're doing is we're relying on the weak learner to deal with that. So in practice, what you would do is you would typically have, you would take a learning algorithm, you would design a special purpose learning algorithm to use as the weak learning algorithm. Okay, so let me give an example. I'll give an example of this in a minute. Okay, so maybe I should skip. Well, okay, so this telling us stuff about AdaBoost, that AdaBoost is actually very closely related to all these game theoretic notions. And although we only talked about the training set, a lot of these ideas are useful in understanding how the algorithm generalizes as well. So let me give a concrete example. So this is an application that was done by Viola and Jones to this problem of detecting faces in a photograph or movie. So again, you're just trying to take photographs like this one and say, is this a face or not a face? So Viola and Jones used boosting for this, used AdaBoost for it. And whenever you use AdaBoost, you have to decide what your weak classifiers or weak learning algorithm is going to be. So for the weak classifiers, they just use these very simple kinds of patterns which look for light or dark rectangles in the image. So in fact, on the first round of boosting, this was actually the first weak classifier that they found. And what this means is add up all the pixel intensities in the dark region and subtract all the pixel intensities in the white region, rectangle. And if that difference is bigger than a threshold, say it's a face, otherwise say it's not a face. Okay, so again, this is going to do a terrible job of classifying faces, but you could imagine that it's going to do a little bit better than random. It's taking advantage of the fact that in a face like this, the eyes tend to be darker than the cheeks. All right? Now, it's doing just a little bit better than random, but if you apply boosting and you apply this procedure repeatedly, then you end up actually with a combined classifier, which is very, very accurate and very, very fast. And coming back to these questions about the number of columns, in terms of the matrix, you would have one matrix or one column for every possible pattern of this form. And it turns out that you can actually search over all of those columns in this case, even though there's a large number. Let's see. So I was going to show a demo, but I think I'll skip the demo partly because I'm a little short on time and partly because the demo was impressive when they came out with this work, but now every camera you buy does exactly this. Every camera you buy does face detection in real time, and but this was the first system that could do it in real time and really super accurately. Yeah.
The only thing that I could never understand in this paper is that they claim that they use 46,000 odd features, when actually from a 24 cross 24 image you can get around 1,60,000. They talk about dimensionality reduction and all that, but yeah, I mean that's one thing I could never get from the paper.
Wow, I never checked their counting. I just trusted their counting. Oh, okay. Really? So they counted wrong?
1,60,000
okay. I don't know. Maybe we should take it offline since I wouldn't be able to answer that on the spot anyway. But okay. Okay, so let me quickly talk about these other applications, again, joint with Yoav Freund. So here's a very different kind of learning problem where we're trying to imagine that you're trying to predict whether the stock market, let's say S&P 500 or whatever, will go up or down. So every morning, you listen to the predictions of a bunch of forecasters, who are making their predictions based on the current market conditions. And then based on their predictions, you formulate your own prediction of whether the market will go up or down. And then in the evening, you find out if you were right or not. You find out if the market actually went up or down. So this is a different kind of learning problem because you're making a sequence of predictions and you have the opportunity to learn in between each one of those predictions. And our goal here is to come up with a way of formulating our own predictions which will be almost as good as the best single forecaster. Now you might ask, why just try to do as well as the best single forecaster? Well, this is a starting point. You can make these things more fancy if you want. So this is called online learning. So in general, we're given access to a pool of these predictors. The predictors could actually be people, as in this example, or simple fixed functions or other learning algorithms, all kinds of possibilities. To be concrete, we're just going to think of these predictors as fixed functions of some observable context. So the context might be some description of the market conditions in this example. And then on each round, we get the predictions of all these predictors, make our own prediction, find out the correct outcome. And what we want is for the number of mistakes that we make to not be much more than the number of mistakes made by the best predictor. Okay, and so this is different than the previous learning problem because training and testing are happening all at the same time. And also, we're making no statistical assumptions. The data could even be chosen by an adversary. It doesn't have to be random. Again, we can formulate this as a game. So Mindy gets identified with the learner now, and Max is identified with the adversary. The adversary is the one generating the data. And so we can set up the matrix where we have one row for each predictor and one column for every possible context. Again, the number of contexts might be extremely large. And we can set up this matrix, the entries, to be 1 if a particular predictor is wrong on the context and 0 otherwise. Okay, don't worry too much about the details, but it turns out that this game is exactly the same game as in boosting, except that we've reversed Mindy's and Max's roles. It's like, in chess, if we're playing chess and then we switch who's playing white and who's playing black. It's the same game, we've just reversed the roles. This game, which is the natural game for this online learning problem, is the same game as the one used for boosting. Okay, so we can just immediately get an analysis if we apply MW to this game. We get the weighted majority algorithm back from this, which I said MW is actually a generalization of. And we get a bound on the number of mistakes of the algorithm compared to the number of mistakes of the best predictor. It just falls right out of our analysis. And what's nice is that the regret is only logarithmic in the number of predictors, so we can afford to have these huge families of predictors. Okay, so here's a little example of this. So we applied this to the penny matching game. So in penny matching, we're imagining it played between a human and a computer. So the human and the computer each choose a bit, or 0 or 1. If there's a match, the computer wins. If not, the human wins. So it's kind of a mind-reading game, because you're trying to predict what your opponent's going to do, and at the same time, you're trying to be unpredictable, so your opponent cannot predict what you're going to do. Okay, if you just play randomly, you'll win exactly half the time. It turns out to be really hard for humans to play randomly without actually flipping coins, which somebody forced me to do once, to play this by actually flipping coins. Okay, so right. So the way we set this up is we played MW, and then we had a family of these natural fixed predictors that just look at recent history. So each one is really simple, each one of these fixed predictors. But when you combine them, you get something that does pretty well. You can try it out yourself over here. Okay, so here's, this was played about 12,000 times on the web. So this is the way we set it up was you play until one side or the other reaches 100. So if you look at the rounds won by the human minus the rounds won by the computer, that's a number between minus 100 and 100. And if you're on this side of 0, that means computer wins. So you can see that the computer is doing much, much better than the human. It really does a good job of predicting what the human is going to do. And one of the things we notice is that the slower that people play, the better the result. Okay, so the faster you play this, the better your chances of losing, turns out, which is probably because when people start playing fast, they get into a rhythm, which is really easy for the computer to predict. Okay, so let me talk about one last application to apprenticeship learning, work with Umar Syed. Okay, very different kind of problem. So here we're trying to learn a skill, like trying to learn to drive in a toy world. So imagine we're controlling this blue car, and there are these other red cars. I'll show you an example of this in a minute. And so you can set this up as what's called a Markov decision process, where you have state, which are the positions of the cars, various actions. You can steer left, speed up, slow down. And then there's a notion of reward. So you're trying to go fast without crashing and without going off the road. That's actually 3 goals. Okay, so the goal is to find a policy, a way of behaving, a mapping from states to actions that says for any state, what action should I take next? You're trying to find such a policy which will maximize your long-term reward. That's the problem. Okay, and this is following on work by Abil and Ung. They noticed that when the reward is known, when you know what the reward is at every state, the optimal policy can be found using standard techniques like value iteration, policy iteration. But in many settings, the reward is not known. Like in this case, we really have 3 goals: go fast, stay on the road, and don't crash. But how you combine those into a single reward is not so clear. And this is a very practical problem in these kinds of settings. So we might not know the reward, but we might have these reward features. And we don't know how to combine those reward features into a single real valued reward function. So we're assuming here that there is a true reward, which is some convex combination of these features, but we don't know what it is. And so we want to learn that convex combination. And there's one more element of this problem, which is that we assume that we get to watch a human expert doing this. So in that case, the goal is, on the one hand, to imitate this expert, and at the same time to try to improve on that expert, if at all possible. So once again, we can formulate this as a game. Okay, we can formulate this as a game where we say that our goal is to find a policy so that the improvement over the expert is as big as possible for all possible reward functions. So we don't know what the reward function is, but we know that it's a convex combination of these reward features, and we want for all of them that the improvement should be as big as possible. So again, we can formulate this as a game. The rows are identified with these features. The columns, we have 1 column for every possible policy. Once again, a gigantic set of columns, a gigantic number of columns, 1 for every policy. And it turns out that when we set up this matrix, the optimal policy will be exactly the max-min of the game. And so we can again find it using the MW algorithm. Turns out that the hard part is choosing that 1 column. On every round, Max has to find that best column. It turns out you can do that just by using standard algorithms for when you know the reward. You can use value iteration, policy iteration, whatever. Okay, so this one I will show a demo of, and then I'll be done. Okay, so so just look at the first row. Okay, so we're going to start out by looking at an expert. Okay, so this is a so-called expert driving the car. Okay, so this expert, this human, is actually doing everything as badly as possible. So it's going as slow as possible. It's going off the road as much as it can, and it's deliberately trying to crash into other cars. Okay, so our apprentice tries to imitate this expert while actually improving on it in every way possible. So when we do that, it will do better. It will drive a little bit faster. It actually stays on the road, and it actually makes some attempt to avoid crashes. Okay, so here's a more interesting expert. Okay, so this one doesn't move, goes as fast as it can, but at least it never goes off the road. Okay, when we run our algorithm on it, it's also going as fast as it can, never goes off the road, but it makes some effort to avoid crashes. Okay, so let me, Okay, so to conclude, I presented this MW algorithm for playing repeated games. And we saw that it can also be used to approximately solve games. And then we saw a whole bunch of, or 3 applications. One was to boosting, where we saw that some really key insights and algorithms for boosting are actually all game theoretic. That boosting itself is a game theoretic problem. And then we looked at online learning, where we saw that in game theoretic terms, the game that's used is actually the same as boosting. So there's this connection between boosting and online learning through game theory. And then finally, we looked at apprenticeship learning, which is a different kind of problem, an entirely different kind of problem, which also turns out to be solvable as a game. If you want to do more reading, let me shamelessly plug this first book, which is a book I finished recently with Yoav on boosting. Even though the book is about boosting, it actually includes most of what I talked about today. There's also this other excellent book by Bianchi and Lugosi on online learning and games in particular. And then these were the articles that the work was based on. I'll stop there. Yeah.
This game framework
Uh-huh.
is just taking previous work and showing that you can cast it all as game, or you did derive some better algorithm in some of the 3 areas that were known before because of this testing these as a game.
Okay, so in the online learning case, the game playing algorithm was actually based on weighted majority algorithm, as I said. So the online learning work certainly came first. AdaBoost was actually derived through this by looking at things in this way. We actually started with weighted majority algorithm, generalized it to games, and then we saw that it could be applied to boosting. So AdaBoost actually historically came from this. And then the apprenticeship learning also came by applying this algorithm. So Abil and Ung had previous work before ours. They kind of proposed this model, and they had a particular algorithm. And so Umar and I, our contribution was to apply this game theoretic algorithm to solve the same problem. Actually, it's a slightly different problem because we were actually trying to do better than the expert, not just imitate the expert, but actually do better. Okay. Any other questions? Okay, Jen.
So you went through this last example pretty quickly, and I was just wondering if you could comment a little on how challenging it was to actually develop the apprenticeship learning algorithm. You know, once you had the idea to use multiplicative weights, you know, is it just a straightforward application of multiplicative weights, or is there a real? Is it hard to actually adapt this to the
Well, it wasn't hard for me because Umar did all the work, but what else is new in advising in terms of the technical details. But I think it was fairly straightforward, but what he noticed was that you could actually go beyond just what the expert was doing, and so I think that that was a new thing. And also to, this idea of noticing that you can use value iteration as the subroutine which chooses the individual columns. So, the most immediate algorithm that you could get was fairly direct, but then, yeah.
So I was intrigued by your game where the computer wins against the. So could you maybe develop even a lie detector that way, because the computer.
Wait, so what's the idea for the lie detector?
Well, because when you lie, I mean, there is a certain pattern of the way you lie, so the computer discovers that.
I don't know.
Or if you try to play the computer against the.
I don't know much about lie detection, so.
Thing, right?
Yeah. I don't know. I'm not aware of anybody who's tried that, but I imagine lie detectors could probably be improved using machine learning in general, but I don't know. It's kind of a creepy application. I don't know. Yeah.
So like in the game playing scenario or the portfolio selection scenario, as you have mentioned that, we always compare our algorithm with the best fixed strategy with hindsight.
You always compare what? Sorry?
With the best algorithm, with the best fixed strategy with hindsight. So I'm always wondering why we don't compare to something else. You have said that there are minor tricks. For example, you compare with a strategy that can change itself for constant time. They obviously just diminish when you think about recent calculating. But in your last section, you said that you can actually perform better than best expert. So I'm thinking whether it can be like that, show that generally we can have a better.
Yeah. Well. Okay. So if in terms of the strict game playing setting, forgetting about the apprenticeship learning. So in the game playing setting, if you want to do better than just a fixed strategy, like I said, you can create an entire family of strategies and compete against that family of strategies. So there are much more general techniques that can be used there. In terms of the apprenticeship learning, the reason we're doing better than the expert is because of the way that we set up the game. So we set up the game in such a way that we're actually trying to maximize the gap between how well the expert does and how well our learning algorithm does. So it has to do with how we're setting things up. It's a little bit hard to explain without seeing the technical details. But it's still the same algorithm and the same analysis that we're using here. It's just a matter of how we set up the game.
So I'm wondering, is there any proof that saying you cannot perform really much better than the best fixed strategy?
Well, yeah, that would. I'm not sure how you could prove that, but maybe. It would be hard because like I said, you can set it up so that you are competing against something bigger than just the single fixed strategy. I just haven't shown that to you. Okay, good. All right. Well, thanks again.